Okay, I think we can go ahead and get started. Welcome to our first Distinguished Speaker Series of the Spring 2024. Um, our speaker today is Richard Day. He will be presenting his talk called Risky Business, What Level of Risk to Mission Success is Acceptable? And just to give you a brief bio for Richard, Mr. Day is a former NASA senior executive with an ongoing commitment to the successful development and operation of complex systems. At the Goddard Space Flight Center, he led nationwide teams in development of state-of-the-art space systems. He's co-chaired the steering committee for mission assurance improvement among the major U.S. space agencies and aerospace corporations during his tenure as chief of mission assurance for civilian and national security space programs at the Johns Hopkins Applied Physics Laboratory. He's also served as the Applied Physics Laboratory Deputy Chief Quality Officer for all the diverse mission areas of the laboratory, serving strategic national priorities. And lastly, he's created and actively teaches an innovative graduate level systems engineering course here on high reliability, mission assurance, and engineering leadership to achieve mission success. So I hope you all enjoy his talk, and I'll open up to him. Thank you.
Thank you, Zoe. And thanks everyone for the opportunity to speak with you today. I will get my presentation up, a few slides to help illustrate the topic. And what we'll do is acceptable risk is a deceptively simple but very complicated and poorly executed concept. So are you seeing my full screen slides now?
Oh, nope, they have not loaded yet.
Okay. Sometimes it takes, oh, I know, hang on a second. Let's try it this way. That should be better in a minute.
Looks good.
Great. Thank you. So as I was saying, acceptable risk is a really misunderstood concept and very poorly executed, in my opinion, across the industry and various industries. So through some case studies this afternoon, I'd like to kind of frame the topic and see what your thoughts are. So I think what's missing is grounding the expectations of stakeholders in a shared context. Often the wide variety of stakeholders on a program or any endeavor have different levels of expectations around risk and may not fully understand what's involved and what the likely outcomes are and so forth. So that's what we're going to try to talk about this afternoon. Apollo 13 is a great start for this conversation. Many of you are probably very familiar with the story, especially through the Tom Hanks movie, but the actual details are not as well known. So I'm going to quickly go through some of the details. Just a little bit of terminology. When we talk about the command module, where the astronauts spend most of their time on an Apollo mission, is circled in the diagram there. The service module has all the expendables and propellants and things that are needed for the journey to and from the moon. And the lunar module is what actually would land on the moon. And you know, it was good to see the commercial landing recently, our first US moon landing in 50 years, and we'll be back soon. So 80% of the way to the moon, Apollo 13 had a pretty catastrophic explosion of one of the oxygen tanks in the service module. And as you can see from the picture, it blew off one whole panel of the service module and caused a lot of damage inside the module. The astronauts' oxygen supply vented out to space and was gone in 3 hours. That was also key to their ability to produce water, electrical power, and they also lost the propulsion system. So with this explosion, it was no longer an opportunity to land on the moon, and the mission became how to bring the astronauts home safely. And it's part of that context that the phrase "failure is not an option" has been sort of promulgated, which represents kind of the theme of mission control and a lot of my thoughts on space flight and other high risk endeavors. So we'll try to frame that a little bit more as we go. So since this was a series of missions, there was an oxygen tank that was removed from Apollo 10 for modification, went back into stock after being modified. But as it was being pulled out of Apollo 10, it was dropped a couple inches. Passed the visual inspection, and everything seemed fine, and it was not segregated from use. But the inspectors and engineers were unaware that the fill line used to fill and empty the tank had been jarred internally, and so this flaw went unnoticed. And then later, when it was time, this tank was used and installed in the Apollo 13 service module. So during ground testing, the tank did not empty properly. And that should have been a clue, but unfortunately it wasn't. And instead, the creative engineers developed a workaround to empty the tank because they had been filling it with oxygen and it wasn't emptying for one of the ground tests. So they decided that, well, hey, this tank has heaters in it. Let's just turn on the heaters. That will heat up and boil off the oxygen, and we'll empty it that way. And so that's what they did. And very, very creative, out of the box kind of thinking. Unfortunately, they missed a few things. The story goes further back. The tank heaters were originally designed to operate on the 28-volt bus that's used in space. But in order to reduce ground processing time, they added an additional requirement to the vendors so that this tank would also operate at 65 volts on the ground. And so, this sort of brings up a lesson about the need for rigorous configuration control. So North American Rockwell was the prime, and they passed along the specification to the sub Beech aircraft and for the original tanks, and then issued a revision 3 years later to add the second voltage requirement. Beech dutifully ordered the new thermostats, but did not change the tanks already built. And this gap went undetected by NASA, Rockwell, and Beech. So adding to the contributing causes, the tank normally operates in the very cold temperatures of space, and the thermostat was basically designed for those applications and would turn off at basically room temperature. And even the temperature gauges on the ground were only designed to read up to room temperature, since mainly they're worried about cryogenic temperatures. However, because of this voltage problem and the way they were used, the heaters kept on the ground for hours, emptying the tank out, the thermostats welded shut, and the tank temperatures on the ground reached over 1,000 degrees, and that damaged the heater wire insulation inside the tanks. And all this went unnoticed because the monitoring systems couldn't read anything greater than room temperature. So in retrospect, there's a lot of clues here that you would have liked the team to pick up on, but they went unnoticed. So that brings up the reminder to be alert for subtle indications of anomalies. We have several mishaps in the space world where there were subtle indications of anomalies on the ground, but because of operational pressures or one-time occurrences, these weak signals of failure went unnoticed. And so we like to have our teams have rigorous engineering curiosity and attention to detail. I think the Defense Science Board said it well a decade or so ago about how unforgiving space is. It's basically a one strike and you're out kind of environment. So accountability is important when these things happen. And it's nice to see that the leadership of NASA and the flight director took accountability, as you can see in this statement. So we can ask ourselves, was this an acceptable risk? Were the gaps in good engineering judgment and best practices, really worth the risk? And of course, this is part of the learning process over time. And NASA in particular, a lot of other organizations involved in these kind of endeavors, pride themselves on trying to be learning organizations. And so, particularly for this kind of close call, there's very intensive review, a very formal report by a Blue Ribbon committee, and action items to address the findings and changes to try to improve the processes that would have prevented this. So that brings us to the operable definition of risk, which is the combination of the probability of experiencing an undesired event and the consequence or severity of the undesired event were to occur. And when I speak about risk, I'm talking about the probability of future occurrences. A lot of organizations kind of mix up the definition of issues and risks, and it's important to keep those separate in my mind. The issues are real things that have happened and they need to be addressed, whereas risks are future issues that you're trying to prevent. And so I think that's a foundational concept for risk management. So let's talk a little bit about the Forrestal aircraft carrier during the Vietnam War. This is a very famous mishap, and maybe you're familiar with it. During the heat of the Vietnam War, very high operational tempo, a lot of pressure to keep the planes flying on their sorties, and and many other contributing causes to the mishap that I'm about to explain. What happened was that there's a lot of safety concerns when you're dealing with ordnance, and there were two groups functionally assigned with the responsibility of controlling the safety inhibits for those ordnance. Both groups felt the pressure and wanted to contribute to improving the operational tempo. So independently, without talking to each other or to their superior officers, each one decided, hey, we can remove our inhibit faster and earlier in the process, and that will move things along faster. The problem was that both groups removed those inhibits, and that was unknown. There were some design problems and other complicating factors. But what happened is there was a power surge on one of the F-4 Phantoms, and a rocket launched spontaneously and across the deck of the carrier, striking another plane. And oddly enough, that plane was piloted by Senator John McCain, just as a historical note there. And so what happened was a major fire on the aircraft carrier. A lot of ordnance exploded. And then additionally, the sailors were poorly trained in the safety practices and how to firefight this kind of fire. And so a lot of the early firefighting contributed to the expansion of the fire rather than containing it. Ultimately, 134 dead, 161 injured. And was it worth the risk? Was it an acceptable risk for those inhibits to be reduced by the different groups involved? Another thought is this is a NOAA weather satellite, hundreds of millions of dollars worth of instrumentation to monitor our weather. The weather you see on the news at night is and on your apps. A lot of it comes from these kind of satellites. And who thought it was a good idea to let it fall to the ground? Um, this is just like many mishaps when you fail for silly reasons. Would you believe that the contractor skimped on the number of bolts that were used to fasten the spacecraft ring at the bottom there, which you can see pointing to the left on the bottom of the spacecraft, keep it fastened to that turnover dolly, the white fixture there. So normally that would be bolted to that white fixture. But with multiple programs going on at this facility with similar hardware and just one set of bolts, one team borrowed the bolts to use on that other system. Then on a Saturday morning, when the crew came in to rotate this spacecraft from vertical to horizontal, they skipped important steps in their written procedures, and the QA inspectors signed off inappropriately without actually the lead for the operation and the QA inspector were both supposed to visually inspect that the bolts were in place, and neither did so. So this was the result. And you can imagine the embarrassment of the contractor facility, the embarrassment of NASA and NOAA in having this happen, as well as the great expense to refurbish, and all the expense in the investigation of how this could possibly happen and how can we prevent it again. So another example of unacceptable risks being taken at various levels of the organization. And while the overall success rate of NASA and other space programs is very, very high, well in the high 90s, there are these notable mishaps that really cause us to think about how adequate our risk management processes actually are. The Mars Climate Orbiter is a famous example. This is the kind of thing like Hubble that makes the nighttime comics very happy, gives them lots of material. How could NASA and the contractors confuse metric and English units? The real issue was much subtler than that. It was more about how they were working internally on their various systems, computing errors and trajectory and that kind of thing. But at the high level, it was a major disconnect in keeping consistency of units and team communication. And this is the kind of thing that should not go wrong. Likewise, the Genesis probe crashed into the desert after an amazing mission to capture stardust, basically, and was supposed to be landed safely on Earth with the help of some parachutes and a Hollywood stunt helicopter that would snag it on its way down. But instead, the drogue chutes never opened, and it just came crashing down at high rate of speed. Fortunately, a lot of the science was able to be preserved, but again, this in particular NBC, if you want to look on YouTube, you can really find a pretty scathing network news report on this. None of these things are the kinds of risks that we want to our reputation and to our program success. In this case, the problem was they were reusing some electronic boards from another similar mission, and the board in question had a G switch sensor that would have detected the deceleration coming through the atmosphere if it was oriented properly. But in repackaging that computer board for the new mission, they lost track of the importance of how that should be oriented with the spacecraft coordinate axes, and it went unactivated because it was pointing in the wrong direction. There was even a test that could have caught it, but and that was a centrifuge test, which can be a very expensive test to mount the system on a big centrifuge. But that would have given the single direction acceleration needed to test this out. But a creative engineer decided that, hey, I can do the same thing so much cheaper on the bench with an oscilloscope, and I'll just lift the box and put it back down. And if I get a signal on the oscilloscope, then I'm good. Yes, the G switch was proven functional, but by lifting it up and putting it down, they were not checking the proper orientation of the relative to the spacecraft coordinates. So again, not an acceptable risk to the program. As a program manager all those years, what I worried about most, what kept me up at night, was realizing how complex the overall system is, how many suppliers I have, how many things could go wrong at various levels of assembly. What if a technician who's soldering a board at a contracting facility halfway across the country is having a bad day and produces a cold solder joint that goes unnoticed, and that puts a flaw in my system that never gets noticed until it gets into orbit. And those are the kinds of things that the Defense Science Board was referring to about all the things that are going right can be undone with one simple thing that's not. So in the risk identification process, which is so key to risk management, it's not about just putting everybody in a room and having a brainstorming session. Well, that's helpful. And these are the kinds of questions you want every member of the team to be asking themselves all the time, as well as using more sophisticated system engineering methods to systematically analyze what could go wrong, failure modes, effects analysis, simulation tools, and so forth. So one of the things that, in addition to these past mishaps that I've been speaking to, specifically Genesis and Mars Climate Orbiter and ones like that, Columbia was also important in my career. I wasn't involved in the mission, but it's when I became responsible for trying to make sure these kind of things would not happen in the future. So I got promoted out of the greatest job in the world, leading these programs, doing spectacular space science missions, and then to the executive roles of trying to make sure we have processes and checks and balances to stop these embarrassing incidents from occurring. And so one of those was Columbia. And that gets a little bit more specific in what we're talking about acceptable risk. So as you recall, in 2003, we lost Columbia, one of our few space shuttles in our fleet, as well as all 7 astronauts on board. And just like Challenger a few years earlier, it was a preventable loss. And that's what makes it so tragic. And these kind of problems, when they occur, are nearly existential in scope, because the program gets grounded for years while we try to do the recovery efforts and the whatever we need to do differently in the future. There's questions about funding, about appropriations. Why are we even doing this in the first place? So all those existential kind of things come up. And if you think of 3 Mile Island and Exxon Valdez and other incidents like that over the years, New Horizons, you realize that a lot of these major mishaps cause existential problems for industry. And in this case, risk communication and governance structure were key issues. So oddly enough, this problem was foreseen in the design process, and the engineers were extremely concerned and even put very specific requirements in the early stages. And they're listed here for you. The foam on the external tank, the big tank that the space shuttle is mounted to during launch, because it's full of temperatures at fluids at cryogenic temperatures, gets very cold. The humid air in Florida, condenses ice on it, and so that ice will come off during the process, and so the launch process, and so that was foreseen as an issue that we need to prevent. We need to prevent the buildup and shedding of the ice and other debris like the spray-on foam that is used for insulation. So you can see that the requirements were to prevent this from happening. However, look at the flight history. 14 flights over and prior to Columbia had significant damage, and there was no flight. You can see the histograms for all the different flight numbers. No flight had zero debris and damage. So it's right from the start, the requirement was not achieved, and it became a normalization of failure, and got lucky for many flights. Became mostly thought of as a ground processing turnaround problem. How many tiles got damaged and how long it's going to take to make the repairs before we can refly the shuttle. Another way of looking at it is here's some of the flights with the significant damage, and you can see how on STS-35 there, NASA called it the safety of flight issue, and also a reuse or turnaround issue. But over time, you can see that it evolves into unexplained and even accepted risk within the experience space, in family, accepted risk. But really, it wasn't an accepted risk. As we'll see, and certainly in retrospect, it was not a fully accepted risk. And before you can accept a risk, you need to really understand it. So the Blue Ribbon Committee that studied the Columbia accident and for and reported to Congress and the administration, it was pretty scathing. NASA has not followed its own rules and requirements on foam shedding and continuously worked on the problem, but the requirement was never met on any mission. And even though it initially was considered a safety concern, it rapidly evolved into in-family, no safety of flight, and accepted risk and other means of rationalizing the failure. So when we're analyzing a risk, we need to really consider the full situation of that. It's not enough to just identify a risk and put it on a top 10 list. We need to analyze what are the potential causes of the risk, what's the accident scenario, the cascading events that could cause such a problem. How can we estimate or frame the probability of occurrence, a time frame perhaps of vulnerability, and how bad could it be if the risk materializes? Even after the accident, it still took a while for NASA and other observers to really grasp that a piece of foam, think of a foam cooler as you're driving down the highway, flying off of the back of a truck and hitting the car. Depending on the circumstances, probably the foam just dissipates and there's no damage. But if you increase the speed and increase the mass of the foam, the density of the foam, it's actually a pretty significant impact. So it was only through testing and demonstration that after the fact that people really grasped the severity of the situation. So another way to look at the concept of acceptable risk is the New Horizons mission to Pluto. The APL mission that just brought us extraordinary insights into Pluto and is now bringing back information at the edges of our solar system. I believe it still holds the record at 36,373 miles per hour as the fastest human object to leave Earth orbit. And you know, that was an amazing feat. And that also ties into what we're going to talk about. To achieve that escape velocity, and you know, which is normally 25,000 miles per hour, to be so much above a normal escape velocity took a very large rocket. And so this was an Atlas V, which is a bigger rocket than you would normally think of sometimes for a spacecraft of this size. Had a relatively narrow launch window, so that it could make its shortest trajectory going at that speed to arrive. You know, even at that speed, you know, it would still take 9 years to arrive. You know, one of the longest, along with Voyager and others, just the longest cruise time to get to your destinations between the planets. So the launch date was really a consideration, as it is for many planetary missions. And then just to, like a lot of our programs, complicated organizational interfaces, and I'm sure many of you have these kind of interfaces within the programs that you support. So those three verticals of the science, people responsible for the science mission, those responsible for building the spacecraft, and those responsible for the launch vehicle. The science mission and the spacecraft fell under the Science Mission Directorate at NASA headquarters, and the launch vehicle came under the Space Operations Mission Directorate. Marshall Space Flight, even though this was an APL mission, the program management was Marshall Space Flight Center's New Frontiers program, and the launch vehicles were managed by the Kennedy Space Center Launch Services Program. The respective contractors were Lockheed Martin for the launch vehicle, APL for the spacecraft, and Mission Integration and Southwest Research for the majority of the science mission. So the Atlas at that time was a relatively new vehicle. We always like to you take such an important science mission, you want to make sure you have a robust success record on the launch vehicle. This only had 7 successful launches before New Horizons. And it was this heavy configuration with 5 solid rocket motors to reach that speed. This particular configuration had never flown before and had a rigorous set of requalification tests, all very good things to be doing. Unfortunately, 4 months before the planned launch date, there was a catastrophic failure of a fuel tank during the final stages of this testing. And so that caused a lot of attention and a lot of investigation, a lot of inspections, a lot of testing, and so forth on the part of the launch vehicle, contractor, and program office to really understand what was going on. The launch vehicle contractor in this contract medium was responsible for primarily responsible for the failure investigation. And NASA, so it's more of a launch service. NASA certainly had leverage as a customer to request data and get the contractor's cooperation, but it was solely the contractor's investigation from a formal point of view. So the situation evolved, lots of testing, lots of meetings, lots of discussions. And then ultimately it was with those launch windows, it was really the point in time where a decision had to be made on whether to launch it or not, or miss those launch windows and cause the significant delay. Complicating things was that there's a small amount of nuclear material for the radio isotope um, um, thermal generators that generate the electricity. Since it's so far from the sun, you can't use solar panels. So whenever there's a launch that has any nuclear material on it, it does cause additional processes to be involved, and additional consternation from those that are concerned that if the launch vehicle exploded, it could, spread radioactive material in the atmosphere. Um, the actual devices themselves are, tested and thought to be explosion proof, so that risk is thought to be well managed, but it's still a sort of an overhang on these kind of missions. So the contractor, the launch services program manager, all became under the decision that they'd done all they can and that they thought that the vehicle was safe to fly. We have this process, which is, I think it's really a best practice in NASA, where and the Air Force, where all the leaders of the organizations involved, the contractors, the government organizations, have to sign a certification of launch readiness. And it's a nice formal process that culminates at a final launch readiness review shortly before the launch, and gets the final launch approval. It's a great process, not perfect, but just having the situation where the representatives of all the companies have to actually formally commit that they're ready to launch is really a best practice that probably could be applied in some other areas as well. So when it came down to voting at that final launch readiness review, despite all of the discussions, analyses, collaborative work, there was still a disagreement. In the voting process, the Launch Services Program at Kennedy voted go. The Kennedy Safety and Mission Assurance Organization voted no go. The representatives of the Chief Engineer's Office, who are matrix to this organization, also voted no go. The program authority at headquarters voted go. The headquarters chief of safety and mission assurance voted no, and the chief engineer voted no. This is a very rare occurrence. Usually it's more clear cut. Even the associate administrator voted go, and it's rare, especially for this kind of robotic mission, for the associate administrator and the NASA administrator themselves to be personally involved. But because of this, the importance of this mission, and the fact that it was known that there was going to be likely disagreements, the NASA administrator, the top political appointee himself, was also present. And that's what's so important about this case study. It all came down to him to make the final break, to break the tie, basically. And when you think of a political appointee, can you imagine the headline, the responsibility of, if this mission failed, despite your safety and mission assurance chief and your chief engineer telling you don't do it? So it really, I think, took a lot of strength and clear-mindedness in order to make a decision based on that political kind of framework, knowing what the headlines could be. But the administrator voted to go, and that's fine. But what was so great about it is the way it was done. On the back of that certificate of launch readiness, the administrator personally wrote the statement that you see here. The Flight Planning Board understands the residual risk and the mitigations that have been taken along the way. The risk, in the view of this Flight Planning Board, which I'm chairing, is understood and acceptable. I recognize and acknowledge the independent inputs, the independent risk ratings provided by the technical team of Safety and Mission Assurance and the Chief Engineer's Office. And it's my assessment that the efforts in mitigating the risk and the rationale for flight provides the highest practical probability of mission success. So this level of accountability and transparency is the lesson here for acceptable risk. The launch was successful. The mission has been enormously successful, but certainly it was not guaranteed. But we all take risks at various times and various programs, and this was a very thoughtful and well-considered risk, but was as important as the accountability and and formal acceptance of the risk. So the way this ties into a risk management process, if you look at the ISO 31000 guidelines for risk management, there's, I guess the most important part to look at is establishing the context, right? So when you set up a risk management process, what is the context that this process is applicable to? We have our normal risk assessment, identification, analysis, evaluation aspects, the mitigation efforts, the ongoing communication and consultation, the monitoring and review, so forth. But the foundation for that is the context. And on the simplified version I came up with, you can see how important the acceptable risk context is, because it informs that identification, that analysis, that evaluation. So if not, what are you identifying and analyzing and evaluating to if you don't have a context for that? And that same context needs to be used by the decision makers to decide whether the mitigations are adequate, how much resources to apply to those mitigations, and ultimately whether to accept any residual risks that result from the remaining mitigation things that are undone and the risk that is remaining. So that's the lesson of these case studies, is to understand what kinds of things can go wrong, try to have the best practices and processes in place to prevent them, but also have an acceptable risk context that decisions can be, analyses and so forth can be framed against when a problem surfaces. So one of the best definitions, I think, of acceptable risk, I borrowed from one of the NASA program and project management top level documents, which is deceptively simple, as I said at the beginning. The risk that is understood and agreed to by the stakeholders so that no further specific mitigation is required. And this is exactly the example in the New Horizons case study that this what it says was done. The challenges are, of course, having a full and accurate understanding of the risk, making sure it's communicated. Unlike Columbia, unlike Challenger, there was not good communication of the actual risk of launching, and then having actual accountable acceptance by the decision makers and everyone who has contributed to the risk mitigation. So with that kind of, an alternate kind of definition is when you think of safety, performance, reliability, expectations that everyone has as stakeholders, what level of risk can be tolerated. And when you think of who those stakeholders are and the kinds of things that they may be worried about, you're worried about public safety, the safety of the team, the safety of the flight crew, how critical and unique is the mission? Is it a once in a lifetime science opportunity that will just be lost for a decade or more? Or is it an operational mission that has to be achieved? What is the financial investment? A lot of the programs right now, the trend is to all these small satellites versus large expensive satellites. But there's still these kind of discussions and decisions that need to be made. Protection of high value assets, environmental protection, political considerations, and public perception. And all these stakeholders have different perceptions on what's an acceptable risk. And maybe many of you have experienced how the risk tolerance seems to evolve from the beginning of a program when it's being sold, or when the budget is being developed and it's smaller than everyone would like in order to accomplish the mission well. You'll hear a lot of talk about, oh, we're accepting that risk. You know, that we're in this business to take risks, and that's fine. But as the years pass and that mission is built, the investment is made, and it gets close to launch and time operations and time to prove it out, sometimes those same people that were voicing the you know, oh sure, we can accept that risk, they're the ones that get the most conservative about this. So be aware of how that risk perception and communication can evolve over time, and sometimes the accountability can get shifted if you're not careful about the acceptance of risk. So with those thoughts, let me just do, one thing that's evolved over the years is, and many of you have seen versions of this risk communication matrix. Keep in mind it's a communication matrix. It's not a decision matrix. It's not a analysis matrix. It's just a way to try to portray the relative risk of various risks on program with respect to each other's, to help with some prioritization efforts. But it doesn't mean green is always good and red is always bad, because you have to have your context, and your context is going to define what qualitative or quantitative parameters would go into these different levels of probability and consequence. And be aware that a lot of times program managers will try to game this process because they know a red risk is going to get them a lot more attention than they want, maybe even canceling the program. And so there's this tendency to understate the risk. Or contrary, if you want to try to persuade that you need more resources or need another organization to do something, you might escalate their risk to try to bring more attention to it. So keep in mind how a risk matrix should be used, what it should mean, and that's part of the context of acceptable risk. And so now I'll open it up if there's any questions or comments.
And you can throw your questions in the Q&A at the bottom, or type them in the chat if you can't access Q&A. And we are happy to answer those. And I know Austin just answered the first question we have, but the recording of this will be posted on our events webpage, usually in a couple weeks or so. So you can always go back and watch this again. Yeah, please feel free to throw your questions in the Q&A or chat if you need to.
Well, good. Hopefully I answered all the questions along the way.
Okay, well, it was wonderful. Thank you so much for giving us this talk, Richard. This was really quite fascinating, and I hope everybody else enjoyed it. And again, you can always watch this again online when we post it in a few weeks. Have a good night, everybody, and thank you, Richard.
Thank you.
Oh, we do have a couple questions. They're just thanking you, saying you're great.
Oh, thank you all. Thanks for taking the time this afternoon.